Sorry, I have a problem here. Okay. Let us proceed. Now, in the next part, we will see how to test. And so testing, of course, is important to see what the performance of our product is, what the quality is, and what the reliability is. And here we look for reliability. And it is important to know that what are influencing parameters. So in fact, we want to stimulate failures, and the most stimulating, let's say, physical influences on failures are temperature, temperature changes, temperature gradients, mechanical shock, vibrations, and on the other hand, internal operating conditions like voltage, current, dissipated power, because it increases the temperature over the environmental temperature, and then environment also comprises humidity and climate, and also there can be some chemical agents. For instance, in a car we have the fuel, we have the oils, we have hydraulic liquids, we have coolant, and so on and so on, and all of these act on our electronics and all together can degrade reliability. Okay, this table is maybe quite impressive. You do not have to learn by heart, but again, it shows what are relevant test methods according to the most important standards for electronic devices, which are JEDEC, military standard, or AEC, which is Automotive Electronics Council. And all of these standards are very similar. In fact, the initial standard was a military standard. Later on, the JEDEC standards were derived. And still later on, this automotive electronics companies derived standards from the JEDEC standards. In fact, I do not know why it was so important, but each of these had specific requirements. So here, this was the military, the US Air Force mainly. The JEDEC is more for private companies, and AEC is for automotive. Okay, so we can see we have temperatures, temperature cycles, temperature shock. So this already shows us this is a low frequency cycling, that is a higher frequency cycling where we have temperature transitions just in the second range. We have mechanical shock, that means something is dropped. Or imagine we have electronics in an aircraft and the aircraft has a hard landing. You must not expect that in such case, let's say, the printed wiring boards fall out of their compartment or such a thing. So electronics have to proceed being operational. On the other hand, besides such single mechanical shocks, we have often vibration, especially when electronics are mounted directly to an engine or to a motor. For the electronic parts, power cycling is very important. So some motor is turned on, turned off, and so on. And we have a driving transistor, and that driving transistor has always dissipated power, and that power heats it up, for instance, by 100 degrees or so, and that again can lead to fatigue. Then we have moisture and climate. Unfortunately, that is not constant condition, but here we have a strong influence how fluctuations of temperature and humidity in the climate are. And the chemical media, and what is always important is a soldering cycle. So if you do soldering, that leads to a temperature shock of approximately 260 degrees centigrade and within a few seconds. And that temperature shock can do significant damage to our electronics. And that's the reason why before we do all of these tests here, we always have a soldering cycle to our electronic devices. Also, I would like to note that here these test procedures are on the level of electronic devices, so single components. And when we regard what happens during that, we can say what is the resulting failure. We can have interconnections which break, so electrical opens. We have the die attachment, so it is soldered somewhere, it's falling off. We have package defects like cracks or hermeticity is lost, like here. We have external leads which can just break due to fatigue, for instance. We can have corrosion, which is mainly a problem to metal, but which can also be a problem to certain plastics. And generally, when we have high aspect ratio structures, these are very sensitive against mechanical shock and vibration. Yeah, so if it's a thin and long structure, it will always deform very strongly, like take a ruler, fix it at one end, and then it will vibrate in a strong way when you touch it. We can have cracking of chips, and what is always very important is that electrical parameters of our device can be degraded. Okay, generally, when test conditions are selected, it is clear that these test conditions must be representative of the operational conditions. And all of the field relevant failure modes must be stimulated. On the other hand, that tells us, for instance, when there are no chemical media to be expected, then of course we can drop these tests. Or when there are special chemical media expected, then specifically for these solvents, for instance, or for these acids, we must test whether this can have an influence on reliability. The test times must be sufficiently long. So again, what is sufficiently long? We know from the technology qualification when we have to expect failures, and the test time must in some way, let's say, representative of the application. So that means, for instance, if the application is 3,000 hours, the test times must be in a way that we can be sure the product will be failure-free for these 3,000 hours. That doesn't necessarily mean we have to test for 3,000 hours. We can also do accelerated tests to shorter times, but again, we must be sure that this testing is representative for the lifetime and the field application. And what is also important is that generally the failure data on which all of this is based must have sufficient statistical significance. On the other hand, when we do just the final end test where we do not expect failures and where we do not allow failures, of course, 0 failures cannot have statistical significance. Okay, here is just a list of the JEDEC standards, just to show you how complex this is, and that is just on the device level. And now we can look for different tests here. For instance, we have temperature tests, which can also be operated. So that is typically bias live, for instance. So we have a voltage on the device, and we can just have no operation, just high temperature storage live, for instance. On the other hand, we have high temperature continuity. That means it is operated. Here is such a chamber we use for temperature shock and temperature cycles. There are differences. Temperature cycles means it's slow, so we can have a gradual transition. We can have a holding time here. On the other hand, when we have a temperature shock, we just change from a hot to a cold chamber within seconds. But for bigger parts, of course, it always takes some time until they adjust to the temperature. So that's an exponential transition. Nominally, it's below 10 seconds transition, but in the end, depending on the mass of the specimen, the transition time can be significantly higher. So we have temperature shock, temperature cycle, and also we can have some cycle which is more or less representative of some field application. For instance, imagine a car. It is heated up quite fast, so it maybe takes 5 to 10 minutes up until the engine is at the end temperature. But when we turn off the engine, it takes several hours until it is cooled down again. So in that way, we have for such temperature cycles different possibilities how to test, but temperature shock and temperature cycle in that way are standardized tests. In the phase of technology qualification, you typically take samples at different cycles. For instance, just as an example, 250, 500, 750, 1000, 1500, 2000, 2500 and 4000 cycles. That means you look here, are there any failures among your devices, and how many failures do you have? When you do that testing on such devices, first of all, it is important to know when is a device failed. And there are several definitions of failure. One, of course, is the device is dead, or it has a short circuit, or it has an open circuit. Of course, that's a clear failure. On the other hand, it is important to know that even when a device is still operational, it can just operate in a wrong way. I would like to give you an example. Some years ago, I did a consultation for a company, and that company was building anti-brake locking systems for motorcycles. And unfortunately, this system had failed, and there had been severe accidents because the front wheel of the motorcycle was blocking, and of course, in that case, the driver will fall down to the ground and can be seriously injured. Okay, what was the reason why that anti-brake locking system failed? And this is a hydraulic system, and that system has an internal pressure, and you need a pressure sensor for sensing this. And in fact, due to a misconstruction, during operation, the 0 point of that sensor could change. So that means normally if there should be a 0 pressure indicated, now it indicates a certain pressure because the 0 point is no longer okay. And that was the reason why this complete anti-brake locking system had a malfunction, and these accidents resulted. In the end, that means even if the device is not dead, if it just gives wrong values, that can be dangerous, and that can be a severe safety aspect. And in that way, functional tests are very important. For instance, for sensors, you first do all of the parameters, for instance, sensitivity, offset, and so on, linearity, extract these parameters. Then you go through all of the reliability testing, which I was showing you in the table, and then you do the functional testing again. And what is necessary, that the initial parameters due to specification are still met. Yeah? So it doesn't help you if a sensor, which is crucial for life, is changing its sensitivity, its offset, and so on during the lifetime of your car. And in that way, the complete system malfunctions suddenly. It is not really failed, yeah, but for instance, a control mechanism doesn't work properly anymore. But here, based on that second functional testing after reliability testing, a decision must be taken: is the qualification goal achieved? Again, that is here on the device level, but in a similar way we must do it on the assembly level or on the module level. But first of all, now let's come back to a little mathematics. And the most simple data on reliability is the failure rate. So, as we have seen, if the specification is not met anymore, it's a failure. And how is the failure rate estimated? That means we have a certain number of specimens, N. And these are tested for a certain time, TA. And after that time, we look how many have failed. So N failures divided by the number of devices in the experiment multiplied with the test time. That gives us the estimator for the failure rate. So it's an estimated value based on the original data, and that is the failure rate. The failure function, that is the total fraction of failures, is the failure rate multiplied with the time. That is only valid for small numbers of failures, and that is also only valid for relatively short times. But here we can say that here n times Ta is the test effort. So you can test them simultaneously, you can test them after each other. In the end, that's the most simple description of test effort. You can have different test strategies, and then the test effort is computed in a somewhat different way. Okay, here that's the estimator. But on the other hand, we have already seen we have some probability for our failure rates. So we have seen we have some probabilities which were given of 60% and 90% probability. That means you want to be sure with 90% probability that the failure rate is lower than a certain boundary value. And here you must give certain failure rates, and these failure rates must be higher than the failure rate you get from your initial test. Why is it so? Here you do not know how much you can rely on these data, because you only have a few failures from a certain test effort, and now you must take into account more factors. And one of the factors for that statistical probability is how many failures you had. And in that way, we can say this estimator, for instance, lambda 90%, is some factor K3 times this measured failure rate. And K3 in the test of that, in the case of that test strategy, is computed in a certain way, which is 1 divided by 2n. N is the number of failures, times chi-square distribution of 2 n plus 1 and 1 minus alpha, and alpha is the error probability. For instance, when alpha is 10%, then 1 minus alpha is 90%. So, okay, so that is the so-called confidence level, 1 minus alpha, which is 90%, while on the other hand, the significance level is the 10% complementary. Okay, but now let's ask what is the chi-square distribution. We must say you find it in some tables, you find it in Excel. And I have just computed some data. For instance, you want to have a confidence level of 90%, and you have 0 failures. Even in that case, you can give a chi-square value, which is 1.8. Of course, that doesn't seem to make sense, but if you have 1 failure, you have a chi-square value of 4. You have n is 1, so you have 4 divided by 2 times 1, and that means in that case for 1 failure K3 is 2. In that way you can see how you have to multiply your measured failure rate in order to give a failure rate with a certain confidence level. And that is important because you want to be sure that your device doesn't exceed a certain failure rate. On the other hand, it is also important that when you want to that when you have more and more failures in your investigation, first of all, that's not good because the failure rate generally will be higher, but on the other hand, your statistical confidence will be better. Yeah? For instance, 118 divided by 98 is almost 1. So you could say when you have many failures, that means your case 3 approaches 1. So in that case, you can roughly take your measured failure rate as a failure rate for that certain confidence level. What is important when you do testing, you first of all need a certain number of failures in order to compute a failure rate. That is important. On the other hand, when you do lot testing, that is in the phase of production. In that production phase, you take from the thousands of devices, you produce 3 lots, and each lot has 77 components. And now when you do the testing here, for instance, high temperature operation, then no failures are allowed. And again, that shows us clearly the test time and the test conditions are depending on which phase we are. When we are in the technology qualification, we want to know what is the failure rate. So we need failures, and we have to test sufficiently long in order to know we have at least a few failures. When we do lot testing, that is a lot which is from a production which is directly sold to some customer. We must take from time to time such lots with 77 specimens or devices, and here when we test, no failures are allowed. Again, with 0 failures, no realistic failure rate can be determined. We can only assume we are better than something. On the other hand, we have seen failure rates are only computed in cases where we assume we have an exponential function. And in that way, when we have, for instance, an increasing failure rate or also a decreasing failure rate, we need to employ another function, and we have seen it is the Weibull function. So let's say beta is larger than 1. We have an increasing failure rate. We have so-called wear-out failures. While on the other hand, when we have B, so smaller than 1, we have decreasing failure rate. And now we want to know the parameters of the Weibull function. So that is the total fraction of failures. And that is defined by 1 minus e to the power of t divided by tau. That is a characteristic lifetime to the power of beta. And so we want to know what is beta, and we want to know what is tau. The tau is something like an average lifetime of our specimens. Now we do a testing, and for that testing we have two data. One is the time. Let's just say 1, 2, 5, 10, 20, 50 times 100. So 100, 200, and here we record how many failures we have as a total. So that is the total of failures. So we have, for instance, here 1, here we have 2, we have 6, we have 10, and here let's say we have 18, just to give you an idea. And what we also must know is what the n is. How many samples were in the investigation? And now using that formula, we can say that is a small correction factor we use, and in that way the failure function can be when we say in percent, of course that's 0%. Let's say n would be 100, then it would be 1.7 and so on, and in the end it's something like 17.8 or so, 9.75 percent. So in that way it is almost the 1, 2, 6, 10, 18%, but a little lower, again approaching it, because that correction is necessary. It's not so important, but the data fit better. And now we plot this over time. So here we have log t, and here we have f of t, and we plot the data, and of course the number must be increasing, and in that way we have a linear graph in that plot. But we must say the scaling here is non-linear. Yeah? So you could say the scaling is in a linear way, that it is more compressed around this mean value. And the reason can be derived in a certain way. If we take this Weibull function here and we put 1 to the other side, we can say 1 minus f of t is e to the power of minus t divided by tau to the power of beta. And when we take that, now we take away the minus, we can say e to the power of t divided by tau to the power of beta is 1 divided by f of t, or 1 divided by r of t. Then we take the logarithm, and then we can see tau t divided by tau to the power of beta is ln of 1 divided by 1 minus f of t, or to make it a little simpler is minus ln 1 minus f of t. Now again, we take again a logarithm, and then we can say beta times logarithm of t minus beta times logarithm of tau is ln is a logarithm of minus logarithm 1 minus f of t. So here it's log or ln t, that doesn't make a big difference, and that here is this transformation, what we plot here. So we have this transformed y scale, but on the other hand we can say if we plot this parameter here against the logarithm of time, we can see that this slope is always the beta, and when we set t is equal to tau, we can just see that this is valid for 63%, or yes, f is 0.632, and in that way we can get the two parameters of a Weibull function. So again, to summarize, we have to perform tests. At certain times, we look how many have failed in total. We do this in a table. From the table of time and numbers of failures, we derive this probability, which is the failure function. And the failure function is plotted, but it is not plotted in a linear way, but it is plotted as this logarithm of minus logarithm 1 minus f of t, or logarithm of minus logarithm of r of t. And from the slope we get the beta, and from 63% here at this axis we get the tau. And in that way, we have performed these data. We can do it in a graphical way. We can do it in a regression analysis. But the most important method is just the maximum likelihood analysis, which is performed here, which, according to mathematicians, is the most dependable version of getting these parameters. So here we can again see y is beta times x minus beta times ln tau, and x is the x-axis and beta is the slope, and that is the offset. Sometimes something happens that when we want to analyze such time, for instance, we get some information that we do not get a slope, but we get something like such a curve. Again, we have this Weibull parameter, and here we often have a offset, which is t 0. That means the complete process of degradation starts only after a certain time. For instance, take the time of a car it was in operation. So you know the date of production and you know when it broke, for instance. If you do such data, you might observe that you do not get a linear Weibull graph, but you get some minimum value. For instance, the tau could be the time where the car is not yet sold. It is produced but not yet sold. Especially in times of overproduction, that could be several months, even sometimes half a year or so. You have transport times, and you must subtract these initial times from your time you use in your Weibull analysis. Generally, Weibull analysis has, for field data, has several things which you do not really know. One is this T0, so you do not know the difference in between production and start of use of that car, for instance. On the other hand, you do not really know how much, what the number n is, the produced, because not necessarily all that were produced will really come into operation. Some are still in storage, for instance. So the n is unknown. And what is also important is, of course, that all cars are used under different conditions. So you mix up a lot of application conditions, and of course that will also have an influence on the scatter of your data you get. But in the end, it can be very helpful. And now, how can we use this? Again, here we have a Weibull plot. We have the lifetime in hours. And we have this failure probability, as you can see here, that this nonlinear behavior on the y-axis. And you would like to do an optimization, and that optimization would be for a car, for instance. So we're talking here about, let's say, 2, 3. First failures are allowed only after 3,000 hours. And how can you do that? When you initially start here, for instance, you find out you have this initial design. You want to optimize it, and of course you can work on it, and you can also you can always try to improve. But the disadvantage is you can test always for very long time, and 3,000 hours is roughly 4 months. Okay, we are going here to 10,000 hours, that is 1 year. Okay, you design a car or anti-brake locking system, and every optimization cycle takes you a year. Okay, in 10 years, your newly developed product will be in the market. Not helpful. What will you do? You accelerate tests. You have the initial design. You build it, you find out you are here on that curve. Now you do accelerated tests. Accelerated tests are harder. More acceleration, more G values, more temperature, more power you use, and so on. And you have that curve here. And you do accelerated tests. And then stepwise, and here these tests only take few hundred hours. And now stepwise you can increase your design until you think it is good. Between here and here, you have an acceleration factor. What is it here? It is something like, let's say, 30. Is it correct here? That's 80 to 1500 to 1600. Okay. 20. Okay. Now you have improved, and now you take this curve here, which is good, so I make it in a green color. You have an optimized design, and again you take an acceleration factor is 20, and now here we have 200, 300, 400, and that gives you roughly 8,000 cycles you can get here. So that means you have optimized a design using accelerated tests. You reduced the effort for testing roughly by a factor of 20 from test times. Of course, the optimized design must again be checked, so you must be sure that this acceleration factor and this acceleration factor are equal. But in that way, you have a strategy based, first of all, on the Weibull curve, and the second is based on acceleration factors. And in that way, you can reduce the test effort significantly, and you can improve your design. Again, my question could be, which phase of your product development will it be? So I would say one of the phases where it is important is the technology development, or it is really the product development, because in the product development you do not want to know all of the let's say details of your design, but you just want to be sure that your Weibull curves are dependable. Okay. Maybe we skip this, also the acceleration we have seen. For the rest of the day, we will just look at a few other aspects. One thing which is important is electrostatic discharge. ESD is a phenomenon which kills a device or which does a severe damage to an electronic device. And ESD is something like, let's say, a high voltage discharge. Typically in ESD you can see something like a small electrical spark jumping, and you can sometimes even feel it when you touch a door handle or such a thing. And now if ESD acts on devices, these devices are differently sensitive. So we have a MOSFET where it's only a few hundred volts, at least for the old style MOSFETs. On the other hand, modern CMOS devices, they can tolerate up to 3000 volts of ESD. Even a thin film resistor can be damaged by ESD in the 300 to 3000 volt range. So ESD is something which can happen easily, and you must avoid it. And there are several methods to test it. It is the charged device model. That is when a device is charged itself and it discharges against an external contact. On the other hand, what is much more severe is the human body model. So a human person, an operator of a machinery, is charged up, for instance, because his butt is rubbing against a plastic seat, so high voltage is generated. On the other hand, in machinery, we often have some potential difference, and that can also lead to ESD at a lower voltage level than human body model, but possibly a higher energy. So for the human body model, we can test ESD. We have 3 classes, 1 to 3. Class 1 means failure below 2000 volt, class 2 means failure between 2000 and 4000 volt, and class 3 means over 4000 volt. For the machine model, we have voltages in classes A, B, and C, and here the ranges are 200 volt, 400 volt, and above 400 volt. How is the testing done? First of all, parametric tests and functional tests are performed, like in all reliability testing. We often do tests at elevated temperatures, because when we do damage to some dielectric, for instance, there will be small creep currents, and these are especially strong at elevated temperatures. Then we take a lot size of 3 components, and we test with positive and negative pulse of all pin combinations. On the other hand, imagine we have 100 pins. That means we almost test 10,000 combinations here. In fact, 9,900 combinations are tested with the both polarities. After that, we do parametric and functional tests, and when it's okay, we proceed with the next voltage level. For the next voltage level, we can use a new device. We can also use the old device, but it's to be on the safe side for your product, it's better to use a new device. And when the electrical parameters lie out of the specified range, or when the device is dead or open or short circuit, this is the ESD failure criterion. Okay, that is something which is important in the qualification of devices. And now we have another phenomenon or a test which is called burn-in or run-in. That run-in is important, especially on the module level. Or on the complete system level. What does it mean when we regard the bathtub curve? That means the failure rate will go down, and that means we have early failures. For instance, that would be 1 year, for instance, of operation, and that means initially we have many failures, and then it goes down until we have here the wear out phase. And that is a big problem, because if the area here is large, that means we have very many specimens which fail, and where, for instance, we have to give replacement or we give compensation. And so what can we do about this? there are several aspects. One is we want to know if it's a problem, and we want to know if it's a problem before we go to the customer. On the other hand, we can say here it's the bad ones that die out. So if we do an initial test in the factory, these initial bad specimens will fail, and they will not fail at the customer's side. So one rule of thumb is that for each step from production to the customer, the costs of a failure increase by a factor of 10. So it's cheaper for a manufacturer if he detects a failure in-house before it is detected at the customer side. And in that way, if you produce systems, you can test these systems on your test stand. For cars, this is also done. For instance, a new car is driven for a small distance, maybe a few kilometers at least. But if there is something which prevents the car from functioning properly, then this will be detected. It can be mended or replaced, and such defective car will not go to the customer. So imagine the car has something you detect in the 5 kilometers driving around the factory. On the other hand, the car would be transported to the dealer gives it to the customer pays, and then he notices his new car, where he's so proud of, will not operate properly. So it's maybe costs of 1,000 euro just to transport it back, or to mend it, or to mend it at the dealers, and so on. It's costly. Costs would be significantly lower when that is done in the factory, and for that purpose we can do a run-in or a burn-in. What is the difference? Run-in means we do this under normal field conditions, under normal operating conditions. Burn-in is accelerated. Yeah? Burn-in means we go into a temperature chamber, or we vibrate it in some way while we operate it. And of course, we have another acceleration factor. Here it is 1, and here the acceleration factor is larger than 1 in the burn-in. And in that way, we can do this burn-in. Advantages are effective elimination of defective samples before sale. Yeah, that's important. The second thing is we have a shorter quality control loop than for field failures. So that means maybe it's only a week or even days, rather than longer times, which can be years or so. It will not help you as a manufacturer when you know that you have done something wrong a year ago or so. Then you have no more chance to correct it or to set up a better production, because all things have changed anyway. Another thing is, it is a good early reliability indicator. So you know what you have to expect when you do burn-in, when you know the beta value and how many failures you have, then you know what you have to expect even when the products are with the customer. It can also improve long-term stability of electrical parameters. So you test for some time, and maybe after that you again do a recalibration. Of course, that calibration is more stable than a calibration on a brand new product. So in that way, you can also monitor offset, 0-point drift, and so. So it's right down here, calibration. Recalibration could be important. It is costly, especially if you just have an anti-brake locking system. You must operate it in some way. So you would have to operate it in a car or in a system that simulates to be a car. That costs thousands just to test one device. It is an end-of-life line test, and it is still not a short-time control loop. Normally, hours or even minutes are desirable. It is also established mainly for thermal phenomena, not for other environmental conditions. And if you want to do it 100%, then the effort is very high. On the other hand, you have not all damaging phenomena which you cover. Again, that's equivalent to this here. Now imagine we have, for instance, electronics for a satellite. Yeah? Costs for a satellite are 200 million euro, and that satellite has electronics, and of course it makes sense to do a burn-in, so it will fail on ground and not fail after the launch of the satellite, because then you would have fireworks for 200 million euros. On the other hand, in that case, even people produce more specimens than are used for that satellites. And for instance, they take electrical parameters and then they take the best one to be launched. Okay, that is burn-in, and burn-in is a very important strategy for improving reliability, especially when you have early failures. Okay. In the next week, we will deal with failure analysis. That is, how can we see what went wrong physically and what tools do we have for this. Okay, thanks for your attention and see you next Tuesday. Goodbye.